Right. So, we talked about the combination of the first and second laws of thermodynamics, and we discovered that you could write them down as dq is Tds, assuming that we are talking about processes which are in quasi static equilibrium all the time, when this is equal to that, and this is equal to du plus pdv minus mu dn and so on here. Now the question is, what happens in a state of thermodynamic equilibrium, any state of thermodynamic equilibrium. I said already that the basic point about thermodynamics is that you have U expressed as a function of the internal energy expressed as a function of S V N, for instance, for a single component system, or S could be expressed as a function of U V N and so on. And in a state of thermal equilibrium, what happens is that this quantity is at a minimum. In other words, these thermodynamic variables have values such that they minimize this energy here, or they maximize this S, and that is most easily seen in terms of a picture. So if I were to draw a picture with S coming out there, and let us say U going here, and then all these other extensive variables V, N, etc. I do not have enough axes to draw all these things, then this represents some kind of surface in this space, and the surface would look roughly like this. Just very schematically, it would look like a convex surface of this kind, such that in a thermal equilibrium state, if for instance you looked at an equilibrium state in which the entropy is kept fixed at some point, then it would correspond to a section of this kind, and let's do this better. A better representation would again look like this, exactly as I drew before. And if you looked at a section of this, here is S and here is U. If you looked at a section of it by cutting it in a perpendicular section, for instance, I am not very good at drawing this, then you have a state on this surface which is at a maximum value of the entropy. On the other hand, as far as cutting it in this direction is concerned, it would correspond to a minimum of the entropy here. So you have an equilibrium state is one where either this is minimized or that is maximized, the way it is drawn here. So that is the idea behind thermal equilibrium state. Now it depends on the external conditions always. What are the variables? Had I chosen a field variable here instead of a state variable like V, had I chosen pressure here, or had I chosen the chemical potential here, then these things would be different. It is not this quantity that is minimum or this quantity that is a maximum in those thermal states, and I will give an example very shortly. But the idea is that thermal equilibrium corresponds to the minimum, or in a certain case, in the case of the entropy, a maximum of a certain thermodynamic potential or state function, if you like. Energy is easy to understand because mechanical equilibrium, the energy is minimized, so it is convenient to say that the internal energy is a minimum in the case where U is a function of S, V, N and the other fluxes in this problem. Okay. Now let us go to the case of an ideal gas, which is a familiar instance, and ask what this gives us. So let us look at an ideal gas, a fixed amount of this gas, so that 1 mole say, so that this goes away and we have an equation of this kind, and I would like to know what is the specific heat. As you know, the specific heat under any condition is denoted by C. It is just the capacity of the system to change its temperature on the absorption or emission of a certain amount, extraction of a certain amount of heat. So, it is just dq over dt under conditions to be specified. Now, when the volume is constant, then it is clear that dq by dt is going to give you, this goes away, goes to 0, is going to give you the specific heat at constant volume. Now, in an ideal gas, the internal energy we know is a function for an ideal gas. This is equal to 3/2 n k Boltzmann T here, and its derivative with respect to the temperature gives you immediately the specific heat at constant volume. So, for an ideal gas, this thing here becomes dq equal to Cv dt plus Pdv. And if I keep the volume constant and differentiate with respect to temperature, dq over dt at constant volume equal to Cv here. So, that figures okay. What happens at constant pressure? Well, the same equation says dq over dt at constant pressure is Cv, because I divide by dt here, plus P times dV over dt, but I must keep the pressure constant. On the other hand, for an ideal gas and 1 mole of it, as we have been looking at here, we have Pv equal to RT, which implies Pdv plus Vdp equal to Rdt. At constant pressure, if P equal to constant, then this term goes away and it says P dV equal to R dt here. So, dV over dt is R over P, or this gives you Cv plus P times R over P plus R, which implies that for an ideal gas Cp minus Cv equal to R, a relation which you are already familiar with. But that is part of a more general relation, that dq is Cv dt plus Pdv. It immediately follows that under constant pressure you have this relation, Cp is Cv minus R. One can now ask, what happens if the process to which I subject this gas is not necessarily under constant pressure or constant volume or something in between, such as an isothermal or adiabatic or any other process where the pressure and volume vary in a prescribed manner, they are related to each other in a prescribed manner. So, let us look at a more general case. Let us look at the following case, of which all these are special cases. So, we look at a case where a process, quasi-static process, which means that you go through a succession of equilibrium states such that P times V to the power n equal to constant, and n is called the so called polytropic index. All the while the equation of state is still valid. So, an ideal gas implies that Pv equal to RT for 1 mole. I am now looking at what happens when Pv to the n is constant. So, in the space of P and V, if I plot P here and V here, these can't be negative, so only the first quadrant is involved. Then, as you know, if I put n equal to 1, I get an isothermal process. That is Boyle's law, it says Pv equal to constant when T is constant. So, you end up with this corresponds to, let us draw this properly, this corresponds to n equal to 1, Pv equal to constant. So, this is isothermal, that is an isotherm. On the other hand, you could have also had Pv to the gamma equal to constant, which is an adiabat, and since gamma is greater than 1, so you have a thing like that which says n equal to gamma, that is an adiabat, adiabatic process. you can have a constant volume process, you can keep the volume constant. So you end up with something which changes in this fashion. This is an isocore corresponding to constant volume, and what kind of n would it correspond to? Well, it means n must tend to infinity, because infinitesimal changes in when n is infinity here, this thing dominates out here. So and when n is 0, p is constant, that is an isobar. So you can have any number between 0 and infinity for n, and then you get a so called polytropic process in which n is the polytropic index, anything in between. As you can see, when n increases over positive values to infinity, the curve bends down and comes down till it hits this limiting value. N cannot be negative. If n is negative, it says p is proportional to v to a positive power, which means if you increase p, the volume increases. That violates thermodynamic stability, which is also known to you as Le Chatelier's principle. You increase the pressure on a gas, its volume cannot increase, it must move in the direction of decreasing volume. That is an equivalent way of saying that you are at the minimum of some thermodynamic potential, and I will mention what this is a little later, but it is obvious from this principle of stability that n must only be a positive number. And now I ask, what is the specific heat if the gas undergoes this process here for a general value of n which is positive, somewhere between 0 and infinity? Well, we know the answer already. When n is 0, an isobar, the specific heat is the specific heat at constant pressure. So we know what it is here, this is Cp, and we know what it is here. On this curve, the specific heat is the specific heat at constant volume, Cv. This is 3/2 R for a monatomic ideal gas, that is 5/2 R, because Cp is Cv plus R. Okay. What is it in between? Well, let us look at it, see if you can work this out. So we have Pv to the n equal to constant. That implies that P Np v to the n minus 1 dV plus v to the power n dP equal to 0, or if you cancel out v to the n minus 1, it says Np dV plus v dP equal to 0. Okay. But we also know that Pv is RT, so we know that P dV plus v dP, this quantity, is equal to R dt in general by differentiating this equation here. Okay. So it says v dP is R dt minus P dV, so this implies Np dV plus R dt minus P dV equal to 0, or R dt, or to write it the other way, n minus 1 P dV equal to minus R dt, or let us write this as plus R dt and put a 1 minus sign here. That is the general relation, and now we need to know what the laws of thermodynamics tell us. The laws of thermodynamics tell us that dq is equal to, I do not even need to use the second law, this is equal to du, which is Cv dt plus P dV. Therefore, the specific heat for a given value of n, which I will denote as C sub n, for a given isotropic process, PV to the n is constant, this is equal to Cn by definition equal to Cv plus P dV over dt for this process, for a given n for this process. But we know from this equation that dV over dt for this process, this implies that dV over dt for a given n process, or P times, implies that P times this for a given process is equal to R dt, R divided by 1 minus n. Okay. So that is all we got to put in here, and then the problem is solved. So we have Cn for this process this implies that Cn for such a process is equal to Cv plus R divided by 1 minus n, but this is the same as Cv plus Cp minus Cv divided by 1 minus n, because Cp minus Cv is R for a mole of ideal gas and Cp is gamma times Cv. So this is equal to Cv plus gamma minus 1 Cv divided by 1 minus n, which is equal to Cv times 1 minus n plus gamma minus 1 divided by 1 minus n here, and the 1 cancels out, and therefore I have my final answer which says Cn equal to Cv times, let us write this as n minus gamma over n minus 1. And that is it, that is the general answer here. So we have an expression for the specific heat for a general polytropic process for an ideal gas, 1 mole of an ideal gas, which is Cv times something or the other. Now physical dimensions imply that this thing must also have the same dimensions as dq, energy over temperature, which is what Cv has. So this is a dimensionless ratio here, and that is the general formula, and it tells us that all the special cases should emerge automatically, and let us see if that happens. So let us plot as a function of this index n, let us plot the specific heat C sub n and see what happens. Now at n equal to gamma it vanishes, this thing vanishes here. When n tends to infinity, so let us recall what these things were. N equal to 0 corresponded to an isobar, P equal to constant isobaric process, n equal to 1 corresponded to an isothermal process, n equal to gamma corresponded to PV to the gamma equal to constant, which corresponded to an adiabatic process. Actually I should say isentropic process, because the entropy is kept constant. Remember that is the definition, since dq is Tds for quasi-static processes. If dq is 0, ds is also 0, which means it is an isentropic process, and n tending to infinity corresponded to V equal to constant, which is an isochoric process here. Now let us see what happens here. When n tends to infinity, this ratio goes to 1, and you do indeed get C infinity is Cv, that is what you have here. So that is some number 3/2 R in this case, this is 3/2 R, this is Cv, this point, and that is attained when n tends to infinity. according to this formula. When n is 0, we have here an isobaric process. So when n is 0, you have Cn is gamma times Cv, that is Cp. So this recovers Cp correctly, and Cp is sitting somewhere here. Cp, that is 5/2 R, and it says when n is 0, you are there at this point. When n is 1, that is this isothermal process, it says Cn is infinite. Of course it is, because remember the definition of Cn, the general Cn was equal to dq over dt for a given value of n, and when n is 1, you are on an isotherm, which means T does not change, this goes to 0 and therefore C goes to infinity. So it is very reasonable that at 1 it goes to infinity. This is the point 1, and therefore it starts here and goes off to infinity in this fashion here. When n is between 1 and gamma, this numerator is negative but the denominator is positive, so C is actually negative, C sub n is negative. So it starts off at minus infinity here, crosses this axis at the value gamma, this is the value 1 out here, and it tends, as n tends to infinity, it tends to Cv, the value Cv here. Notice that for no polytropic process can the specific heat have a value between Cv and Cp. This is 3/2 and this is 5/2 R. But it could actually have, for certain processes, it could actually have a value of n which is between which is less than Cv or greater than Cp on this side, depending on the polytropic index that we wrote down. So all the 4 limiting cases, to go back to the PV diagram, here is V, here is P. Remember that if I start at this point and I talk only about the part of the process where the volume increases, then this would be, or increases or remains constant, this would be n equal to infinity, this would be n equal to 0, this is n equal to 1, and this is n equal to gamma out here. Corresponding to these 4 processes, you have specific heats here which are respectively Cp in this case, Cv in this case when n tends to infinity, when n is 1 it is 0, and when n is gamma it should be 0 on an adiabat because dq is 0, ds is 0 on an isentropic, for an isentropic process. So at n equal to gamma the specific heat should vanish, and indeed it does so here in general. So even the simple ideal gas, classical ideal gas, can have fairly complicated behavior depending on the kind of process to which you subject the system. Normally one restricts oneself to isothermal and adiabatic processes, but there is no reason why you cannot consider a more general family of processes such as this process here. One could ask, is there a general relation which expresses the difference Cp minus Cb? We found it was equal to R in the case of the classical ideal gas, but I leave it as an exercise for you to show that the following is true. This requires a little bit of partial differentials and so on, playing around with these differentials, but in general it turns out that Cp minus Cv is equal to, on this side, T times delta P over delta T at constant volume times delta V over delta T at constant pressure. In other words, if you give me the equation of state, which corresponds to saying that you give me P as a function of V and T for a given amount of the gas, then I can compute these partial derivatives, and that is what Cp minus Cv is in general. For an ideal gas it will reduce to whatever we had talked about. This whole thing reduces to R for an ideal gas, but this is the general formula which is valid for more general cases than the ideal gas itself. Okay. Next, I mentioned that you can have other kinds of independent thermodynamic variables, not just the ones that we have chosen, which were S, V and N. You could look at other kinds of thermodynamic variables and keep those constant and ask what is the equilibrium state of the system, etc. So remember that we started with something which said du was Tds minus Pdv plus mu dn. So that is the generalized first and second laws together, and this corresponded to a thermodynamic potential u, which is a function of S, V and N, and at a minimum is at a minimum in a state of thermal equilibrium. So look at the structure of this. It says this perfect differential is a product of differentials. There is T times ds, P times dV, mu times dn. These two, T and S, are thermodynamically conjugate variables, P and V are thermodynamically conjugate variables, mu and n are thermodynamically conjugate variables. So the question arises, suppose this choice of variables is not what I want, I do not know how to control the entropy, maybe I would like to control the temperature. Can I find a new thermodynamic potential which is at a minimum in a state of thermal equilibrium at a given value of T, V and N rather than S, V and N. So I would like to eliminate S in favor of T, in other words somehow bring this around and write it as S dt. Similarly, I may be able to control the pressure rather than the volume. So I should be able to write some other thermodynamic potential in which the differential of that potential involves not P dV but V dP or N d mu for that matter. Is this possible or not? And the answer is yes. This is the way thermodynamics is one of the beautiful parts of thermodynamics. There are other such potentials, they correspond to other kinds of free energies. For instance, if you had as independent variables T, V and N, then the potential that is at a minimum for given values of T, V and N is the so called Helmholtz free energy, which is denoted by F. In the same way you have T, P and N, this is denoted by the Gibbs free energy G. You could have S, T and N here. So you retain this, but you consider you change S, P and N, you change this from VdP from PdV to VdP, then you have the so called enthalpy denoted by H, and then you can also have we change this to P, so you could have T, P and N, that is done. So we did not change this, we changed this, we changed this here and made that also changed, and then you could have a system where and then the internal energy, well you can also make other changes, you can also write it in terms of N d mu here, but since I have not been focusing on change of N, let me not do that for the moment. These are the other commonly used thermodynamic potentials, there are a couple more, but these are the most commonly used ones. So you can either use U or F or G or H depending on what you can control, what are your variables which you can vary and keep constant, for instance. We will talk next about how this and this helps us understand different phases of matter, because that is the next and last topic we are going to deal with, namely the change of state, for which we need a little more information about this.